But he can't be known.
All right, everyone. Okay, it is my pleasure to introduce Grant Gilcrease. Grant will be presenting his work on blocking that he's been doing for the last couple of years. Although he's been here a while, he did his undergraduate here, and he did research in my group then. And he did such a great job that I gave him an offer, and I'm like, please stay, and he did. So he's been doing blocking related work for a while. But for the past 2 years, he's been focused on the Northeast Pacific sector. Yeah, I'll let you go ahead and keep going.
Okay, can you all hear me in the back? Good? Awesome. So thanks for that introduction. I'm going to be presenting on the work I've been doing the last 2 years, looking at very specifically the dynamics and impacts of blocking in the Northeast Pacific Ocean. Just to give us an outline of where we're going to be going with that, I'll give a quick definition of what blocking actually is. I know most people haven't worked with it. I'll look at what its impact is in the Pacific, why we're choosing to focus on this region. Next, I'm going to show the methods that we're using to identify atmospheric blocking, how that compares to some theory that's popular in the field right now. And then I'll show some composite analysis of these blocking events. This will lead to some questions about what's causing those impacts. We'll look at the relation with the storm track using transient eddy kinetic energy and local alliance and palm flux. Lastly, we'll investigate what the covariance with atmospheric rivers looks like, and I'll talk about how we identify those and split them up. So atmospheric blocking is defined as the persistent, quasi-stationary, wide-scale regions of high pressure. These are associated with an anomalous anticyclonic circulation, which is clockwise in the northern hemisphere. Due to their persistence, their wide scale, we see temperature and precipitation extremes as there's the normal flow of the atmosphere is disrupted. We see long-lasting, up to weeks at a time, departures from the climatological weather patterns. This schematic here shows what an actual atmospheric block looks like. On the right, we have normal conditions where you just have zonal flow directly across the Atlantic in this case, versus this is what a block flow is going to look like. So you see, we have this high-pressure system here. The flow is coming in and then gets rerouted north all the way up into the Arctic region, and then has to go all the way around the high to keep going in the zonal direction. So this is the kind of pattern we're looking at. We're going to get extreme disruptions from your typical patterns. You see this cyclone here, if there were no blocking pattern, would continue straight across, hit Portugal, Spain or so, but now it's going to get rerouted all the way up and around, maybe hit Greenland. So that's just kind of the changes and impacts that we see under atmospheric blocking. I'm going to show some significant recent events in the region of interest just to motivate this question a little bit. First, the 2021 February Texas cold outbreak, where the sustained northerly flow off the lee side of the Rockies led to cold air outbreaks throughout the American Central Plains and into Texas. And then also the 2021 Pacific Northwest heat dome that led to record high temperatures for weeks at a time in Portland, Seattle, Vancouver. Many lost lives, persistent subsidence, cloud-free conditions led to those. So with the Pacific Northwest one, this lasted from 25th of June to 2nd of July is when it was considered a heat dome. We saw surface temperatures 15 to 20 degrees Celsius above normal. You see degrees of 116 Fahrenheit, well above record temperatures during this heat wave. The British Columbia Health Department reports 861 deaths during this event, and combined across the Washington and Oregon, there's another 700 or so, so a highly impactful event. Coastal marine die-offs, wildfires due to the windy, hot conditions, dry. Poor agricultural yields, a lot of the fruit farming in Washington was disrupted by this. And then we had snowpack melt in the mountains due to these record temperatures that led to landslide conditions as well. With the 2021 cold snap in Texas, we had there was a block pattern that set up right in here. So persistent northerly flow pushing that Canadian and Arctic air south into Texas. Record low temperatures led to power outages that lasted for weeks at a time. Steering of winter storms that led to some drought conditions in the West Coast and flooding conditions in Canada. You might also remember this as the time Ted Cruz took a trip to Cancun.
I'm sure he does.
So some current theories of what causes atmospheric blocking. The most popular theory among blocking people right now that they're really excited about is this traffic jam theory, where if you imagine the flow of the atmosphere as a one-dimensional flux problem of wave activity, like cars on a road is a one-dimensional flux of just cars, then we consider that there must be some threshold that has to get passed and then all the flux stops. And that's kind of a similar thing as what we see in blocking. There's also a perspective people use looking at it from a PV perspective, looking at Rossby wave breaking or weather regime patterns where they say that the atmosphere falls into idealized specific states. This is very popular in the European sector, looking at Greenland blocking, Scandinavian blocking, things like that. There's a lot of talk right now on the impacts of dry versus moist dynamics. So you can't explain blocking purely from geostrophic flow and a dry system. So what kind of heatings have to occur? What role does moisture play in the maintenance of blocking? And then a perspective I took in my undergraduate work was looking at how planetary wave superposition impacts blocking, where you might have teleconnections from multiple different patterns overlapping to lead to sustained tides in one region. So as I mentioned before, we're focusing on the North Pacific sector for this analysis. You see most of our blocks are going to be set up right in this region over the Aleutian Islands. Not necessarily our Aleutian high, but very highly correlated with it. This region is the second most common for blocking in the Northern Hemisphere behind that Euro-Atlantic sector. And since we're on that West Coast, such high population centers, potential for very heavy economic impacts, cultural impacts, and as I mentioned before, this can be modulated by planetary scale wave phenomena more so than those Euro-Atlantic ones, since you're getting more of a direct impact of linear interactions between ENSO, NJO, teleconnections, QBO impacts on tropical convection and things like that. Previous studies have shown that when you get blocking in this region, cold anomalies form on the eastern side of the Rockies. Those are what's shown in the top panel on the right. This is from Carrera, Higgins, and Kowski, 2004. That figure shows that in blocking days, more than 35% of them experience cold anomalies in the top 10 percentile of the climatology. And then we get warming where we'll have this northward advection. So into the Kamchatka Peninsula, Bering Sea, Alaska, up to those same 30–40% of days under blocks were in the top 10% of warm conditions in the winter season. We also see strong precipitation anomalies, both positive and negative, along the Rockies where there's along the coast, and then also the Sierra Nevadas where you have typically storms pounding into them, and whether that's going to be elevated or declined, leading to heavy precipitation anomalies. Some work that I've done previously showed that La Nina conditions enhance the blocking frequency in this region. That's what's shown here. This is the teleconnection pattern for as observed during La Nina conditions, where red signs indicate positive height anomalies, blue are negative height anomalies. So if you imagine that persistent background pattern throughout a winter season, that's going to make it more favorable for a blocking pattern to set up in this region. And also, MJO phase 7 and a little bit of 6 and 8 teleconnections can constructively interfere with that pattern to increase blocking frequency in this region. More recent work has shown that the type of El Nino event itself can influence blocking frequency in this region, with more eastern Pacific El Nino events versus central Pacific El Nino events. McKenna and Caraperdu have shown that Central Pacific El Nino events teleconnection patterns can greatly lengthen any blocking events that occur, almost doubling them in length. And then also they show that this teleconnection difference is not well represented in any sort of climate models such as CMIP or CESM. So to go into what we're doing for our analysis, we're using ERA 5 extended winter data, so November through March, and we're using data from 1979 to 2019 at quarter-degree resolution. We're doing 500 millibar heights, 2-meter temperatures, total column water vapor, integrated water vapor transport, and 300 hectopascal winds for this. For precipitation measurements, we're using the integrated multi-satellite retrievals for GPM data set. This is at 10th degree resolution. It uses satellite retrieval from the TRIM and GPM eras to get daily precipitation rates. So you will notice some slight differences in the patterns, but generally the same since we are doing that slightly different time frame. The first method we're using to track blocks is derived from Schweers et al. 2004. They use this method with PUD, but we're using it with the 500 millimar height, getting through similar processes. So what we're looking for is closed contours of 500 millibar height anomalies overlapping with each other by a certain threshold for that persistence criteria of 5 days. So that's hitting all of those things that I mentioned as being in the definition of blocking, where it's a wide-scale, persistent, quasi-stationary region of high pressure. After some sensitivity testing, we found that the best thresholds to identify blocks using this method in this region is a height anomaly threshold of 100 meters and requiring 50% overlap across subsequent days of those anomalies. If you see studies with PV using this method, they'll usually use a much higher overlap, somewhere around 80 or 90%. But obviously PV is going to perform much differently under these scenarios. It's much more highly conserved than heights. So that's where this main difference comes in of previous studies with this method. Another method we're using is two-dimensional dipole index for atmospheric blocking. It's calculated using that big scary formula on the top right. Basically what it does is it takes the average height 15 degrees north of a point and 15 degrees south of a point, subtracts them. If that value is positive, it means the heights are increasing poleward. So this is looking for a reversal of the climatological geopotential height gradient. So in this figure, if you imagine that these are height contours instead of theta, you see that it decreases poleward on a given level as one would expect. But if we get a pattern like that green line, you'll see that you end up having higher heights north of lower heights. So that's the main thing we're trying to detect here. To satisfy those criteria I mentioned as part of the definition, this has to be greater than 0 at a given longitude or latitude over a 15-degree longitude span, and that has to persist for 5 days. So after running these algorithms, these are the results I got using ERA 5 data. We get 109 blocking events using the anomaly tracking method and 118 using the dipole index. Each of these have an average length of about 8 days, 825 blocked days for the anomaly tracking, 832 for the dipole index. And after we did this, we wanted to look and see if there was any sort of life cycle. Yeah.
Grant, on the prior slide, does this allow you to discriminate, the one before that was, also in longitude? So how wide are these blocking regions?
Yeah, that is something that we can toy with.
Have you done anything with that, or is that coming later, or not yet?
That is a part of the next step.
Oh, okay.
Yeah. So wanting to look and see if there's any correlation between these two types of blocking events, what's plotted here is just the distribution of all the days tracked by these methods. Dots in blue are using that anomaly tracking method, and dots in red are using that 2D index. And if there were a correlation or a life cycle, we would expect things like this, where it's switching from one to the other subsequently a lot more often than it actually is. So there is some sort of evidence that these are two separate types of events we're tracking. Different dynamics might be at play. So when we do a composite analysis of the geopotential height, this is the patterns we end up getting. The shading is the height anomalies, and the contours are the mean heights during these events. Both patterns show this high pressure system centered over Alaska, extending south into the Pacific. The main difference comes from the location of the flanking lows. So more southwest and then east versus directly a north-south line in that region, where we even see a little bit of an overturning of the flow, like was in that idealized schematic of what it's looking for. So a very different pattern, but still going to be some similar impacts in similar regions. Next is going to be a temperature anomaly composite. Colors are going to be the anomalies. Solid lines indicate positive height anomalies, negative is negative height anomalies, or dash is negative height anomalies. Initial glance, very similar patterns, but some key differences to note. When we look at the contour tracking method, most of the temperature anomalies are going to be advection driven. So along this western flank, we're going to have a poleward advection into the Arctic through the Bering Sea, and that we're going to see highly warmer conditions around 3-4 degrees above average sustained for that approximately 8-day period. So important to know. And then on the eastern flank, where we have that northerly flow, is where we see that cold snap throughout the entire continent. For our other type of blocking with the dipole index, we see much stronger temperature anomalies co-located with each other. With this region, the high is more co-located with those warm anomalies up in the Alaskan region. So co-occurrence of that subsidence and that advection from the south is going to lead to temperature anomalies on the order of 5-6 degrees in magnitude, and then same with the negative anomalies around 5 or so. We also see advection from the tropics up through here with a little bit of an indicator of some warming anomalies, and then some chilling through this pathway along here, leading to some around 2 degrees Celsius cold anomalies in the Pacific Ocean. Since we have this anomalous cyclonic circulation, we're going to have a pathway for moisture and warm temperature to go all the way up from the subtropics into the Arctic, suggesting this could be an important pathway for energy and for moisture to get into there. So an important thing that might play an outsized role relative to its occurrence. Comparing across one another, the main things we see, the magnitude of these anomalies is very different. Still similar cold snaps throughout the continent, and then there is that little bit of difference with the location of that low pressure system, providing a little bit of advection-driven temperature anomalies as well. Next, we'll start looking at precipitation. You'll note the height pattern here is a little bit different. That is due to that different time frame I mentioned before. Shown in green is anywhere where there's a positive precipitation anomaly, and brown is going to be a negative precipitation anomaly. And again, similar patterns, but some key differences to note. First, if we look at using the contour tracking method, this is almost entirely advection-driven. Advection of moisture northward along the western flank, increased precipitation on the southern coast of Alaska, into the Bering Sea in Russia and the western coast of Alaska. Extreme drying throughout the west coast, all along from roughly the Yukon Northwest Territories south into Mexico and Baja California, with this poleward dry air being advected south or southwest off the Canadian area, and disrupting what would normally be the flow of moist Pacific air into that region. When we look at the 2D index, we see a very interesting pattern. Same thing happening up here in Alaska, where you have that advection of moisture, but the drying is much more zonal, is one thing we know. There's this very narrow region where you'd expect anomalous easterlies, as opposed to that wide region of anomalous northeasterlies or so. So that's where you see your drying out. We're considering that to probably be a disruption of the Pacific winter storm track, and we'll go into more on that later. And another important thing to note here is this thin axis of increased precipitation, which we assume to be atmospheric river activity, and some later results will show that that's almost certainly true. So heavy increased precipitation along California, the west coast, decreased precipitation all along the Canadian west coast, with increased precipitation in Alaska and into the Arctic. So comparing between the two of them, major differences, this axis of drying versus this one, the presence of this atmospheric river activity, and then the actual magnitude of the strength of these precipitation anomalies up north is also important to note. In summary of these composite analysis, we've shown that there are significant prolonged impacts to the entire North American continent from this one event occurring in the Pacific region. Polar regions experience well above normal temperatures that are persisting for a very long time. This has potential economic impacts, potential ice melt impacts, and we see precipitation extremes, both high and low, all along the entire West Coast. Potential for flooding, drought, are both possible during these types of events. To explain some of these precipitation impacts, we then investigated the role of the North Pacific storm track, which is shown over there on the right. The storm track is generally the zonal path of preferred propagation of extratropical cyclones across the Pacific. This is a significant source of meridional temperature flux to the Arctic and moisture flux to North America. If we follow on this animation on the right, we see continuously repeated cyclones popping up here and convecting all the way across the Pacific, hitting that exact same region that we saw that those dry anomalies were observed. Because if we imagine that there's an anticyclonic circulation here, rerouting those storms poleward is where you'll get those increased anomalies we saw here. The storm track and blocking are very heavily tied to each other. The exits of both major storm tracks in the northern hemisphere are set good conditions for Rossby wave packet decay and for blocking conditions. This study by Quinting and Vitar investigated S2S ensembles for Rossby wave packet decay and growth. Shown in gray is anywhere where there's Rossby wave packet growth. We see that's largely on the western flank of our two major ocean basins. And the brownish color is where we see decay. So at the exit of the storm tracks, where our preferred regions for there to be a decay of Rossby wave propagation and a setup of atmospheric blocking with all that energy there that can't really go anywhere. We also, current work is showing that the latent heating provided by these storm tracks is important for maintaining blocking. As I mentioned, the geostrophic component of purely dry geostrophic dynamics cannot explain the lack of propagation eastward with the mean flow. So there's a warming along the western flank that acts to kind of slow down any sort of propagation. In our study, we're using transient eddy kinetic energy to define the storm track. This is just a simple eddy kinetic energy. We're using 300 millibar winds. I applied a 2 to 6 day bandpass filter and then just used that equation on the top right. Any region where we see it elevated in the, this is the winter mean, is where we expect to see that mean storm track. And so if you keep that in mind as we show the composites, you'll see that that's almost exactly where we see our dry anomalies. So really high potential for impact when interacting with that really impactful mean state event. We're also going to use the E-vector introduced by Tremberg in 1986 as a version of the local Eliason palm flux, which is usually examined in a zonal sense, but this is generalized to a three-dimensional sphere. The E-vector, as he derived it, has three different components. There's EU, EV, and EW, which each show how the eddies are acting to slow down or speed up the mean state, zonal, meridional, and vertical flow. In this case, we're using their EU formulation, which is shown down here. The important thing to note with this is that any region where there's convergence of these vectors is somewhere that the eddies within the flow are acting to slow down the mean zonal flow, so adding easterly momentum to the atmosphere. And during our blocking events, if we take a composite of the transient eddy kinetic energy and the anomalies, this is what we get. The black contours here are that mean state winter jet that I showed earlier. The gray contours are the height anomalies, just to keep you oriented on where our blocking events are. And then the shading shows the eddy kinetic energy anomalies. We see that for both types of blocking. There's a disruption of the storm track in the actual Pacific right here, but major differences over the North American continent where that doesn't really continue through. For the contour tracking, but for the dipole-based index, we see a total shutdown over the North American continent. Both types of blocking show this poleward rerouting of the storm track up north with this elevated transient eddy kinetic energy in the Arctic region. So suggesting that we're not just evaporating and getting rid of that storm track activity, we're rerouting it poleward, with also a suggestion that some of it is being shown southward during the 2D blocking index. An initial first definition of blocking that some people used was actually looking for these split jet events, not using anything else, just where do we see a split flow of two sustained regions of eddy activity. If we try and look at why this is happening, this is that E-vector calculation with that mean storm track shown. The shading is any region of convergence or divergence, with convergence being shown in blue. We see that there's only one small major region of convergence right here south of the Aleutians for the contour tracking based index. So not necessarily having that entirely zonal impact. Almost no, you see divergence here, for instance, so almost an enhancement of the storm track over the actual continent. But with the 2D based index, we see a total shutdown of the storm track. Convergence all across the entire North American continent into the Atlantic Ocean. So suggesting there is a very different role happening here. And then divergence south of it, suggesting there is a bit of a southward redirection of that storm track, increasing the eddy kinetic energy down there, speeding up the mean zonal flow. Summarizing our impacts with interaction with the storm track, we see that feedbacks with the storm track play a vital process for the life cycle of a blocking event, and some of those previous weather extremes we noted can be highly explained with these rerouting of cyclones of blocks interacting with the storm track. Differences in those impacts of the two blocking events can also be largely explained by their respective impacts on the storm track. We saw heavier rerouting of storms during that dipole blocking event. It's the same place we saw heavier precipitation anomalies, really zonal disruption of the eddy kinetic energy in the dipole events where we saw that zonal band of negative precipitation anomalies. So suggestions that these are playing a direct role with each other. Lastly, to investigate that role of enhanced precipitation in the southern region of the dipole blocks where there was that evidence of atmospheric river activity, we wanted to look at how atmospheric rivers were occurring during all of these blocking events. So an atmospheric river is defined as a narrow region of enhanced poleward water vapor flux. These play an important role in this region. Some estimates have up to 50% of California's heavy rainfall associated with these AR events. We often see this in the wintertime when California's not in a drought. You'll see these continuous pounding of tropical just trajectories of water going straight at California as if they're a magnet or something. In this region in particular, in the northern Pacific, you see two major types of ARs. There's a more Kuroshio extension type, zonally oriented across the entire basin, originating around southern Japan where we see that Kuroshio extension current. And there's also more of a Pineapple Express type with a northwest orientation originating near Hawaii. So these are what's shown above, the mean at IVT during those events or integrated water vapor transport. This is also a significant source of precipitation in those more northern regions of the West Coast, so not just California getting their impacts from these AR events. To get us oriented, this is a composite of the integrated water vapor transport during all blocking events that we've shown so far. The arrows represent the total flux of water vapor throughout the entire column. The colors represent anomalies in the integrated amount of water vapor in the entire column. And then again, we have the heights there just to keep us oriented. We see mostly similar patterns to our precipitation, where you get advection southward, drying out the air, versus advection northward into the Arctic, almost directly across the Bering Strait. But a key difference to note is the strength of these magnitudes across the two different ones. Very strong advection into the Arctic here, very moistened conditions, very dry throughout here. Where we see it is actually moistened during the contour tracking events. And then this strong AR activity is what we were initially seeking to investigate. Total column water vapor anomalies off the scale around 4 or 5 millimeters. So very moistened conditions lasting for those 8 days that these blocking events can occur. So highly impactful as well. To identify any AR activity occurring with our blocking events, we use the image processing AR tracking algorithm by Zhu, Ma, and Sheng, 2020. This uses image processing methods to look at the distribution of elevated IVT, where that might be concentrated. Then it has to meet an identified object, such as this one right here, where we see elevated IVT. Then has to meet narrowness requirements along this major axis drawn, comparing to a minor axis. And it has to be of a certain length, and it has to be of a certain magnitude. I also applied a persistence requirement compared to a blocking event. So anything shown in the next few slides is when these ARs landfall for at least 24 consecutive hours, just to try and get some of those sustained impacts that we might be seeing that might have more potential for damage. So then I split landfalling ARs into 3 different groups. We have an Alaskan, Pacific Northwest, and Californian landfalling regions. You can kind of imagine these as the 3 different bullseyes of where we had precipitation anomalies. We had the advection up here, the strong advection into here through during those dipole blockings, and then drying out here. So maybe looking at, is there a lack of AR activity that's leading to that drying? After applying these algorithms, these are the amount of days that fell under both a blocking condition and had landfalling ARs. A given day is allowed to fall under multiple types of, or multiple landfalling AR types. So looking at the omega blocks, where we had about 811, quarter of the days or so had a Alaskan landfalling AR, a little bit more in the Pacific Northwest, and a little bit more in California. So that California AR is the most impactful and common. Same pattern seen with the dipole one. About a quarter of them have an Alaska AR, almost half have a Pacific Northwest, and then about 2/3 of all dipole days tracked have that Californian AR. Looking across, we see that there is that heavy increase with those Californian ARs with the dipole blocks versus the omega-like blocks. So when we do that same IVT composite for all 3 of these different landfalling locations, there's a lot going on here, I'll walk us through it. But important things to know is that the shape of the ARs are going to be, or the shape of the block is going to influence AR location. In omega blocks, we'll look at how the geopotential height contours are oriented relative to each other. Dipole blocks will look at the pathway for the moisture. So starting off with Alaska, we see this elongated, more meridionally oriented high, more of a pure northward advection of moisture into Alaska, into that region we identified. Very different mechanism occurring with the dipole block. So we have this low here, bringing tropical moisture along the eastern flank through this S pattern, almost like a warm conveyor belt. Yeah, Dan.
Sorry, can you clarify? These are composites of when there is a landfalling ARs during,
Yes.
and there is the...
And the block, yes. So this pathway shows tropical moisture going up the eastern flank of the cyclone through this pattern into the Arctic. Similar pattern we're going to see with all 3 of these, but the orientation of this low relative to the high is what's going to determine whether we get impact in a specific region. When we don't have this meridional stretching of the high is when we see that Pacific Northwest AR. So we did our analysis starting at 30 degrees north and working, or 40 degrees north, working forward from there. So we can have some blocking events that aren't necessarily getting all the way up into that high latitude northern Pacific, more of a along the coast like this. This is more similar to what we got during that heat dome event in 2021. When that happens, you don't get that complete poleward rerouting of the moisture. It more is just getting a little bit rerouted towards that, a little bit north of typical storm track region, which might be more along here. Similar things seen as was the Alaska landfalling ARs for the Pacific Northwest. Tropical moisture along the eastern flank of the cyclone, and then up through the S. Interestingly, the AR activity on average is coming from the south-southeast when it has a Pacific Northwest landfall during these blocking events. And then this one is actually associated with much weaker advection into the Arctic, suggesting there might be some role of drying out along those mountains when these kind of ARs occur. With the California ARs, during those contour tract ones, we see a very amorphous pattern. Actually negative anomalies, suggesting that on your average day, there is an AR hitting California. There's about a quarter of days overlapping between these two patterns, so that might just be a fragment of this picking up. Not a whole lot that can be seen there. But this is exactly what we were looking for when we wanted to investigate these ARs. Direct advection of moisture from the subtropics towards California and into the Arctic, but not along this connected pathway, suggesting, as we saw up here, there might be two different kind of pathways for moisture going on here, or they have potential to connect with each other. In conclusion of my work thus far, atmospheric blocking produces prolonged anomalous weather patterns in the northern Pacific. Impacts of blocking include temperature and precipitation extremes throughout North America. We saw moistening in the north and south of the continent, warming in the far Arctic, and cold snaps stretching all the way down to Texas and Florida. Many of these anomalies are achieved through the rerouting of that storm track along the persistent anticyclonic circulation. And then we saw that the co-occurrence of blocking in ARs is important for determining the regions most strongly impacted by a blocking event. Moving forward with this research, the next step is going to be to develop a year-round database of blocking events impacting the continent. We're going to be looking at blocks in the Pacific, Atlantic, and over the land. And then we're going to toy with some of those parameters that you were mentioning, John. So it's, can we see any differences or sensitivities to these parameters in the detection if we require less persistence, more persistence, a wider block, a different magnitude, and then leave this available for other folks who might want to study blocking in the region. We're also going to potentially investigate the role of blocking as a bridge between phenomena on synoptic scales and seasonal to subseasonal time scales. We saw that correlation with the INSO or MJO, which are happening on those interannual time scales, and also interactions with a cyclone, which is happening more on a weekly time scale. So how can blocking act as a bridge between those two type of phenomena? Lastly, I'm interested in investigating the actual predictability of blocking events as captured by multiple metrics, looking at what might create a forecast of opportunity for a blocking event. These are not currently captured very well in algorithms, so determining what aspect of a climate model or forecast models, what about a block makes it difficult to forecast. I'd lastly like to thank some of the folks who made this research possible. My partner, Abby, who deals with my stress every night and is always there for me. My mom, dad, two sisters who've been there for me my whole life, made this possible. My two dogs, Milo and Ruby, they are my babies. I'd like to thank my professor, advisor Stephanie Henderson, who has working with me since January of 2021 now. I don't know where I'd be in my career without her. Also Dan Beimon and John Martin, the rest of my committee, they've given me some great advice, guided me in my future research. My best friend Kyle, who's not able to be here today, but he's very good to me. Lastly, I'd like to thank everyone, the rest of the friends I made here, all my trivia teammates, and Spencer Strider. Get well soon, buddy. With that, I'll take any questions y'all might have.
Okay, very interesting talk, and so great talk. So you showed that the Bering 2 methods, you have similar numbers of blocking events and duration as well. I'm wondering, have you looked into events and see if they're capturing the same events, but or not at all?
Yeah, so that's a little bit where we were showing with this plot right here. So that I initially thought that might be the case, so that's why I made this. But it's not really what's happening. You see one event being captured only by one index, a little bit of overlap here, but for the most part, there's only about a quarter of all days overlapping between the two indices. And
Building straight off from that, you mentioned regimes early on as a detection method. Do you think that you've detected two distinct blocking regimes with the two different methods where you have them set up? They do look like very different patterns that a regime detection would identify those as two different slopic regimes, and I wonder what sort of signal that you have found two different blocking regimes.
yeah, the regime-based analyses in this region so far haven't really picked up two separate patterns necessarily. They do get an Alaskan ridging pattern and a Pacific ridging pattern, I think is what they call them, but not necessarily these dipole versus zonally patterns like we see here. Yeah.
Yeah, I think one question I had, and I think it's related why also like the composites between the two different indices that you're using look different. I think in the case of the one that we saw on the left-hand side, so the Schwirtz et al., the like contour overlap tracking algorithm,
Yeah.
I think that one picks up different blocking types.
Yeah.
And that's like the biggest difference. So
Yeah.
while we have the other one on the right-hand side, the Massage et al., that just picks up like the dipole blocking index, while the other one picks up omega, dipole,
Yeah,
and
exactly.
the two different flavors of Rossby wave breaking. And I think that this is also the reason why the composite based on that one look more like a smearing out effect.
Yeah.
Because it's just like
Lot of
putting a
things
lot of
together.
different blocking types together in one. So I don't know how to handle that, but maybe you could look at different blocking sub-patterns based on that index and then really compare it like
Yeah.
with the dipole index and maybe.
That is
there's
something I am a
some-
little interested in with the next step, because we are making that database of blocking events. How does it, what kind of biases are we introducing with these indices at the workshop recently? I didn't know there was that much disagreement with folks in the blocking community. So that is something that I'm interested in, is what kind of biases might we be introducing. But I think we've shown that there are separate things happening. So what, and I thought it was going to be a life cycle thing. That's why I made this plot. I thought it was going to be a life cycle, but it's really not really what's happening. Evan?
So just squinting at this plot, I feel like I can see that there are more blocking days occurring towards the end of your winter
Yeah.
season. And I was wondering if you've thought at all about that like interseasonal difference and whether or not one metric over this entire 6 months makes sense, or like do you see differences in blocking over the course of the winter season?
No, that's a good point. We actually heavily concentrated toward the later season, end of the season with the dipole-based index, but not as much with the other index. So again, different mechanisms occurring. Maybe early in the season in November, you don't have that storm tracks as well set up, or the tropical teleconnections as well set up, something like that. So there is definitely something to be said there about a difference within the season. Again, that's year-round database is part of the next step, see what kind of differences might be popping up. Dan?
It was really nice talk, I enjoyed it. I'm always interested in this kind of a contrast between an episodic analysis of something versus more of a looking at like a continuum. Thinking about some of the stuff Marie Madsen's done, a lot of stuff out of John's group with the extension versus shift of the jet. So I'd be curious, I mean, the dipole that you're seeing there looks a lot like just a West Pacific teleconnection or an NPO teleconnection, especially that cooling anomaly, the Rockies, the structures that you see there. And you know, have you kind of looked at your days within that lens as well, just to see how this compares to some of the other work that's been done on that?
I haven't quite done it yet, but that's a little bit of what I'm interested in, is just doing a direct correlation between those kind of indices of EPO, PDO, stuff like that. What's happening in this region that's not being picked up by this, that's still impacting it.
Yeah, and I think what's interesting there is that I don't mean that in a that can guide like the way that you look at what's setting up these blockings.
Yeah.
You have other tools that are other another way of looking at things. You look at say optimal addition conditions or other stuff to kind of back out like what are we seeing? Are we seeing episodic behavior in particular regions?
Yeah, Melissa Braden has some work on optical initials with this basically exact event. And hers was in JL, mostly setting it up.
Yeah, yeah.
John?
Yeah, I think it's interesting too, Grant, so good work so far. I think one thing that seems missing in most of the dialogue here is the jet itself, which I think when you had on your 6th bullet point for future work, I think the idea that maybe blocking is a bridge between subseasonal and synoptic scale events. I think really the jet is the agent of communication between the two, and I think that shows up in your composite differences between these two types of blocks. The overlap block, or the folding over of the geopotential height block, definitely is an extended jet across the Pacific. And I'm interested in whether or not the jet evolution that leads you to a block is consistent between the two types. And if it isn't, what does it say about the disturbances that are being carried along by the jet as they try and set up one or the other of the blocks? Because the other thing that would be interesting to see is a direct reference to the latent heating and the axis symmetrization of low PV that can go on when a cyclone actually makes its way up the western side of the ridge. You mentioned it at the beginning of your talk, but it never showed up again. And I wonder if that's really difficult to do in the tortuous route that some of the EP diagnostics seem to suggest, immediately off the west coast and then bringing things up to Alaska. And then I had one other comment, if you can
Sure.
comment on it. It strikes me that looking at Arctic sea ice in the midwinter, and here we have most of our events late in the winter, is particularly hard to dislodge in the western part of the Arctic basin, so off north of Alaska. Do these events have a big impact on melt? And is there anything that you can say about that?
I haven't specifically looked at melt. I know moisture transport, this is a key player in there. So I'd imagine there's a correlation there, but I haven't looked at that at all.
Okay.
With your first comment, that's something I looked at a tiny bit in my undergrad. I looked at in the concept of INSO versus La Nina jet conditions, and we did see differences of jet extension versus retracting. And I was only using the dipole-based index at the time, but jet extensions versus retractions for a La Nina or El Nino season if there's a blocking event occurring.
Mm-hmm.
So there's definitely something to be done there, looking at if there's a difference across these two indices as well.
Yeah, I think the jet is one of the agents of communication of the very things you're looking for here.
Yeah.
So it's not the only one, but it's one of them. So it's one to keep an eye on. Thanks.
Evan?
I thought the plots you showed showing the E vectors were really interesting, and I really like that as a mechanistic description of what's causing the slowdown, like that there's actually an anomaly in the amount of energy being fluxed in by eddies. And you're showing this as after you've done the composites, now I'm going to go look at what the efflux looks like. I'm wondering, have you or has anyone else gone the other way with it, where you start by calculating what these vectors look like at all times and then using that as your metric to try to understand blocking? And if you can pull out blocking just from looking at it from a jet stream anomaly perspective where you have an anomalous eddy convergence or divergence.
I don't know of anyone who's done that in a composite sense. The original paper, Trenberg, was a case study of a blocking event using that kind of metric. I think there's definitely a potential thing there, looking at potentially regions of E-vector convergence persisting in a region. How might that work?
Yeah, I like this as you're starting with a physical mechanism versus just starting with that 500 millibar overlap. Like that will catch a lot of different events, but you get that smearing, you lose the description of what specifically is going on. So, yeah, these are really cool.
If you try to add another blocking index, somebody in the blocking community might throw a chair.
It's
There's
awesome.
already so many.
Now there are 15 computing standards.
Yeah.
What does this say about the way the term blocking is popularly used?
Yeah.
Like these
Yeah.
two indices are behaving
Yeah.
differently.
Yeah, I went to a Clivar conference mid-March out in Boulder, and that was a lot of people were talking about is, are we even capturing the same events? Are we talking about the same thing when we say blocking in general? And people were like, oh, so we should split it up into different types and different things. And I think you lose some conciseness, and when you do that, the term blocking comes from blocking the mean westerly flow, which is the commonality between these, is you're not getting a zonal consistent flow across the basin, and how does that lead to different impacts. So I don't know if delineating further would smear out some of the commonalities there. That there is a mechanism for impacts here, and that comes from a blocking of the flow.
Which index is better than?
Another person in the blocking community will throw a chair here.
I don't know, I don't know about any of this,
They will
so I'm
find this
just.
video and punch you.
There, I think you know what you're bringing up is that, you know, the common better is a normative term, whereas you're trying to use blocking as just a non-normative term, right? So when you want to, you know, the difference, that if you're trying to come up with some sort of a metric or something, if you want to go to a normative metric, then worry about westerly winds, worry about like precipitation off the west coast or something, you know, instead of something that's more.
I had people come up to my poster in Boulder and just say, I'm going to ignore this side. Because I only use this index, so I'm not going to look at all these. And I'm like, okay, I worked hard on that.
It's a tough issue with the blocking community. I mean, there's been like arguments over what index is better, how you define blocking ever since probably like, I don't know, decades, I don't know. It's every blocking workshop that we've had, it's like, okay, how do we avoid that discussion? Because somebody's gonna get angry and
I would suggest maybe you force everybody at the conference to talk about what they've learned about nature, not what they've learned about their diagnostic.
people get, I
And
don't know,
that would be
people
maybe
get
one way to level it, but
Yeah.
I don't know if it would work. Too idealistic, perhaps.
I mean, again, it'd be like me asking John, you know, what's the best synoptic cyclone? You know
Well,
what I
that's
mean?
easy though.
It's one that comes to snow in Europe, yeah, but I mean, it's like, that's what I mean, it's like, I mean, there are so many different, and again, once you start getting into that normative terminology, you have to define what you're.
Now that Michael's gone, we can't say tropical.
Got that. I have free reign.